In this video, we will analyze a conventional amplitude modulation when the modulating signal m of t is a random signal. In this case, the model for the modulating signal is an stationary random process with zero mean and with a known autocorrelation function and power spectral density and power. The modulating signal with modulation index A, MA, is related with the modulating signal just by this scaling factor, the ratio between the modulation index and the range of the modulating signal. Taking this into account, now the random process that is modeling the modulated conventional amplitude signal is just S of t, where we have the carrier amplitude times 1 plus the modulating signal with modulation index A times the cosine of the carrier. We are going to obtain the mean of this random process, and the mean of a random process can be obtained by the mathematical expectation of the analytical expression of this random process. In this case, we have here the expected value of S of t. And taking into account that the cosine is a deterministic function, we can move the cosine out of the mathematical expectation, and inside of the mathematical expectation we only have the random process MA of t. The expected value of MA is the mean of this random process is 0 because the mean of the modulating process M of t is 0, and therefore the mean of the conventional AM is equal to the carrier. This is the first result. With the same model for S of t, now we are going to compute the autocorrelation function of this random process. The definition, expected value of the product between the random process at t plus tau and the random process at t. This is the expression for the random process at t plus tau. This is expression for t. The two cosines are deterministic, can go out of the mathematical expectation, and the product of these two terms with these two terms is producing these four terms here. The last one is a single term, is the product between these two random processes. Now, taking into account that the expected value of MA is equal to the expected value of MA at t plus tau and is 0 because the mean of M and MA is 0, and taking into account that now the last term here, the expectation of this term is the definition of the autocorrelation of MA, and applying a very well-known trigonometric relationship, the product of two cosines is 1/2 the cosine of the difference between arguments plus 1/2 the cosine of the addition of the arguments. Now we can obtain the final expression for the autocorrelation function. We have this term here, half of the squared amplitude of the carrier times 1 plus the autocorrelation function of MA times the addition of a cosine of omega c tau and a cosine of omega c times 2 times t plus tau plus 2 times the phase. It is straightforward to see that both the mean and the autocorrelation function depends on the time, but this dependence is cyclic, is periodic, with period given by the frequency of the carrier. Therefore, we have a cyclostationary random process, and the power spectral density is obtained by means of the Fourier transform of the time average of the autocorrelation function. To compute this time average of the autocorrelation function is relatively simple, because basically, with this common factor here, we have two terms. This one doesn't depend on the time, so the time average is itself. And when we consider the other term, if we take into account that we have the integral in an integer number of cycles of a cosine this integral is 0. Therefore, the time average of this term is 0, and finally, the time average of the autocorrelation function is equal to this term that we have here, this term. We can rewrite a little bit this term, taking into account the relationship of the autocorrelation of MA with the autocorrelation of M, because if we have this scaling factor between MA and M, the autocorrelations are related by the square of this factor. And finally, the power spectral density is the Fourier transform of this time average of the autocorrelation function. The Fourier transform of A cosine is 2 deltas, and then the Fourier transform of this term times the cosine, with this scaling here, is basically producing 2 shifted replicas of the Fourier transform of the autocorrelation, which is the power spectral density of MA, shifted plus and minus omega c, and each replica has half of the amplitude of the original power spectral density of MA. We have here the final result. Okay, 2 deltas and 2 shifted replicas of the spectrum of the modulating signal with the corresponding scaling factors introduced by the scaling given by the modulation index and the range, and each replica with with a quarter of the squared amplitude of the carrier. This is the power spectral density of a conventional amplitude modulation.